Hi guys, welcome back. So this morning what we're going to have a look at is specific heat capacity. So we're going to calculate the heat change for a substance given the mass, specific heat capacity, and temperature change. I've missed saying this in the last couple of videos, but I really think it's important that you go through and you do your vocabulary words and make sure that you've got those definitions in a place that you can easily access. Because when you guys go back to study for something, like say in 5 weeks time and you go, oh my gosh, enthalpy, what is enthalpy again? I want you to have it all there ready to go, one spot in your book for your revision stuff. Okay, so let's go through. Let's talk about what specific heat capacity actually means. So if I have a gram of water, now water is one of these really cool substances. I don't know what it is about water. It's just it's such a unique compound and it's such a simple compound. But the really cool thing about water, if I was to take 1 cubic centimeter, so each length of this side was 1 centimeter, 1 centimeter, and 1 centimeter, and so the volume of that substance was 1 cubic centimeter, then the amount of volume of this is also going to be 1 milliliter, so nice easy conversion. But for water is actually really nice because of its density. It's actually got a weight of exactly 1 gram for every 1 mil. Okay, so that's a really, really cool thing about water. Now, if I was going to heat this up using my beautiful flame here, let's get some yellows going. Yeah, now that's looking like a proper flame. That's looking good. And let's say I was going to heat this up. So I could put in, so much energy, right? And let's say that this energy is, this temperature of this water is currently at room temperature, so at 25 degrees Celsius. And I'm putting in energy and energy and energy, and eventually I raise this up to 26 degrees Celsius. So the more energy I put in, the higher the heat capacity of this particular substance. Now, water is one of those really cool substances because considering how simple of a molecule it is, it actually has a very, very high specific heat capacity. So it has a very high ability to absorb a lot of heat without actually feeling any hotter. An example of something that doesn't have a super great heat capacity is something like metal. So I used to live in Cairns, right? And it is hot in the summer. And we used to go swimming down at the local pool. And there was 3 different pools. And I was only ever allowed in the big pool when Mum was supervising. And it was this really exciting thing to go in the big pool because you could go jumping off into the one that had the 2 meter depth. And we just loved to do that. But obviously, if Mum wasn't there, we couldn't go there because, she didn't want us to drown. Responsible parent, I guess. Thanks. But every single time we would come back from swimming in the pool, we would always get an ice block and we would always jump in the car. And the first thing that we would do when we would jump in the car, I would always sit on the bloody seat buckle and I would always burn my bum on the bloody seat buckle. And that's because metals are actually really, really low in terms of their heat capacity. So you don't have to add much energy to metal for it to raise its temperature by 1 degree. Whereas if you think about standing in a puddle on a hot day, if you stood in a puddle on a hot day, it's not going to burn your feet or anything like that. If you stood on sand in a hot day, it is going to burn your feet. If you sit on a buckle, it is going to burn your bum. So some things have a very high specific heat capacity and some things have a really low specific heat capacity. So having a look at that, let's actually assign some values to this information. So we'll talk about water because water is one of those really cool ones, the one with the high specific heat capacity. So it has a heat capacity of 4.2 joules per gram per Kelvin. So what that means, it's going to take 4.2 joules of energy to raise the temperature of 1 gram of water by 1 degree. Now I've said 1 degree Celsius here, but here we've used Kelvin. And I sort of want to jump in to explain what the difference between Kelvin and degrees Celsius is. So absolute zero is this idea that nothing moves or everything is a solid. So even something like helium or hydrogen, which are really, really small gases, even those particles would be frozen solid at this particular temperature. So that's what absolute zero is. So absolute zero is when effectively everything is a solid. And that's not quite the exact definition, but I think that's the simplest way that I can sort of say this. And what they actually did to measure this, they were actually using gases, and they were looking at the volume of different gases under different temperatures. And so what they were actually able to determine was you know, so let's say that this was the temp and this was the volume. I'm not sure if that's right. No, I don't think it is. I think it's the other way around. I think that side was the temp and that side, and that side was the volume. That makes sense because the volume is dependent on the temperature. Okay, and so what they did was they measured the volume at particular temperatures. So let's say they started off at this temperature here and going up, as the temperature went up, the volume will go up as well. And so what they kind of did was they worked backwards until they got to this point, this theoretical point where the volume of each gas was going to be 0. Now, the reason this doesn't make sense was because after a certain point, gases condense into liquids. So it's not like the gas has a volume of 0, but it's just like this theoretical idea. So that's why I kind of like to just, rather than saying this whole idea with the gases and the volume and everything like that, it's just easier for us to think of absolute 0 as that point where every single thing is a solid. Now, here's the deal. As scientists, we want to try and construct linear relationships. And the problem that we sort of have with using something like Celsius is that, oh my gosh, there's a mosquito. Sorry. The problem with using something like degrees Celsius is that we have this sort of point, right, where we have, let's say water boils at 100 degrees Celsius, and then we know water freezes at 0 degrees Celsius, and then I have reactions that happen below that, and that's going to happen at a negative temperature. And so if I was going to attempt to graph that graph, you know, it might look something like this because, you know, the negative, it flips it and makes it all weird, and we don't want that. We want just like a straight line, just like we've got in this situation here. So effectively what they said, okay, we're going to make the scale of these the same so that 1 degree Celsius is the same, or the change in temperature of 1 degree Celsius would be the same as 1 degree Kelvin. It's just we're going to shift it back 273 degrees. So effectively, if you wanted to find the temperature in Kelvin, it's just going to be the temperature in Celsius minus 273 degrees. And similarly, if you had the degrees Celsius and you had Kelvin, you just have to add 273 to get it to be the same. So it's this really nice sort of relationship. And now it makes every single thing linear, which is why we've done it. That was a bit of a tangent. I'm just going to clear this and come back. So let's actually talk about what we're supposed to be talking about today. So we're talking about specific heat capacity. So to calculate the specific heat capacity of any compound, it's the amount of energy required to raise the temperature of 1 gram of a substance by 1 degree Kelvin. Okay, so this is the formula that we're going to use. So Q is the total amount of energy that's required. So we have the mass of a substance, we have the specific heat capacity of a substance, and we have the change in temperature. So these are all the units here, and I'll show you how these units sort of work. So the heat energy, the joules, is going to be equal to the mass in grams times by the specific heat capacity, which is joules per gram per Kelvin, times by the change in temperature. So just having a look at the units here, I'll show you what kind of happens. So first things first, these two units are going to cancel each other out, and then these two units are going to cancel each other out. And so that's how we are left with just the joules in energy. Okay, so let's actually do an example now. So 200 mils of water was heated in a beaker. So the initial temperature of the water was 16 degrees Celsius, and the final temperature was 62 degrees Celsius. How much energy was required to heat the water? So the first thing that we know, the really nice thing, like we said about water before, is that 200 mils of water is going to be equal to 200 grams of water. So that's how much mass we have of this particular substance. Now let's calculate the change in temperature. So we can do this just using Celsius because, like I said before, the scale of Celsius and Kelvin is actually the same. It's just we've shifted it back by 273 degrees to make it a straight line rather than having negative and positive values. They're all just positive values from 0. So we can do 62 minus 16, and that's going to give me, hold on, 62 minus 16, 62 minus 16 is 46 degrees. So this change is equivalent. So we can say the change in temperature is 46 Kelvin. Okay, and then what was the next bit of the question? How much energy was required to heat the water? So the specific heat capacity of water is going to be 4.2 joules per gram per Kelvin. Oops, capital K for Kelvin. All right, so let's substitute these values in and let's work out the total amount of energy required. So the total amount of heat energy required is going to be equal to the mass times by the specific heat capacity times by the change in temperature. I really like this formula, by the way. And that's going to be 200 in grams, make sure it's always in grams, times by 4.2 times by 46. And that's going to give me, hold on, let me just pop this in my calculator, 200 times by 4.2 times 46 is equal to 38,640 joules. Now, I'm not sure if you guys are like people who particularly look on the back of food packets or whatever, but usually when we actually measure energy, typically in society we use kilojoules, and the reason for that is because the unit joules are actually really, really tiny. So if you want to, you can convert this into kilojoules, but you don't actually have to because it's not a standard unit. So we can just divide by 1,000, so that's going to be 38.64 kilojoules. Okay, so I want you to have a go now. So determine how much energy is required to heat 72 mils of water if the initial temperature of the water is 273 Kelvin. Hey, so that's the same as 0 degrees Celsius. And the final temperature is 17 degrees. So have a go, and I'll come back with the solution for you after the jump. All right, so I just want to do this last little bit just to show you. So we're going to write out our formula. So the amount of energy required in joules is going to be equal to the mass times by the specific heat capacity times by the change in temperature. So that's going to be 72 grams times by 4.2, because we're still talking about water, times by 17. So just quickly going to pop that into my calculator. 72 times 4.2 times 17 is equal to 5,140.8 joules. And again, if you wanted to, you could convert this to kilojoules. So 5.14, I'm just going to do it to 3 significant figures. So 5.14 kilojoules. But you don't have to do this step. All right, so sometimes what happens is we're given, like when I've spoken about this before, when we do things in the lab, we're always given the mass of something because we can always weigh something on a scale instantaneously in a lab. And then we can go back and work out the moles and everything else later. But when things react, they react in molar ratios. So sometimes you'll have to convert back and forth between specific heat capacity in moles and specific heat capacity in grams. Okay, so just be aware of that. So all you need to do, depending on what you've got, so if you've got the mass version, you're going to times it by the molar mass to get the moles. And if you've got the mole version, you're going to divide it by the molar mass to get the mass version. I've said mass and molar mass about 6,000 times. I've confused myself now. Okay, so we just need to remember that. So what I would suggest you do, I would suggest taking just a moment here to go and draw this diagram in your book, because we're about to use this in the next step. Okay, so enthalpy changes. So we spoke last time or last lesson about enthalpy changes and how the energy stored in the bonds is kind of related to the change in temperature. But they're not exactly the same thing, right? Enthalpy is the energy stored within the bonds. So we can use the change in temperature of the reaction to help us find this value indirectly. But specific capacity is not about energy that's stored within the bonds, right? It's nothing to do with that intramolecular situation. Instead, I'm talking about the ability of something to retain heat. So just be very, very careful of that. But since both of them are related to this idea of the change in temperature, we can actually use both of these informations to find the change in enthalpy of a reaction from the change in from the specific heat capacity. Whew, words. Okay, so to do that, we're just going to use this formula. And the change in enthalpy is going to be equal to the energy required to change 1 mole of a substance, right? 1 mole of a substance by 1 degree Celsius. And something to be very, very careful of here is that this is measured in kilojoules, not just in joules. And again, it's also moles now that we're dealing with. It's not mass that we're dealing with. So again, if we look at the units, that will kind of make sense because the change in enthalpy is going to be represented in kilojoules per mole. And to find that, we're going to divide the amount of energy by the number of moles. So if we use those units, we can see where that formula has been derived from. So to do that, what we can actually do is we can measure the change in temperature using a special kind of machine called a calorimeter. Calorimeters are something that kind of like an insulated system, and if you have enough insulation, then hopefully you won't lose heat to the environment. And so you can use that to then measure the effective change in temperature. Not always accurate, because as you know, like we could have like 6,000 layers of insulation and we could still lose a little bit of heat to the environment. But what you can actually do is you can actually make a very, very simple version of a calorimeter at home. So all you have to do, just need 2 styrofoam cups. You need a little styrofoam lid. I know, terrible for the environment, but styrofoam is a great insulator. And what you do is you stick a stirrer, so like this tiny little spoon here, you stick that into the thing and you make sure that you're mixing that around so that the reaction is like mixing evenly. And then you put a thermometer in there and then you can measure the temperature using that thermometer. All right, I'm going to pause that video there. I'm going to talk about calorimeters and how they're used and how we use this to calculate enthalpy changes in moles in the next video. Talk soon. Bye, guys.